last section of Chapter 1, more application problems. So first up, we would like to earn interest. The key thing on all of these is going to be to draw a table. So let's start by getting a table drawn. On the left side, you always want to put your options. In our case, the two different accounts that we're putting money into. We know one of them is going into a 3.5% account. And then the other one is saying we don't know what we want to put it into. So that's our X percent. And then across the top, you always want to go with your principal, which is how much money you're putting in, your rate, the time, and this is then going to give you your total interest. And it's for your principal times your rate times your time equals your interest. So now let's substitute in our values that we know. So first off, we want to earn $75. We know that $800 is going into this 3.5% account. So that means $800 is our principal for here. Our rate is our 3.5%, but we want that as a decimal. So remember, you've got to move your decimal place 2 spots. Your time is 1 year. So our interest is just going to be multiplying this across, this 800 times 0.035, which equals 28. Next up, our less risky account. We knew we had $1,300 total to invest. If 800 of it's already in here, the rest of it's what we're investing at the percent we don't know. So this is going to be our 1,300 minus 800, which means we've actually are investing $500 in this account. We don't know our rate, so once again that's a variable. Time 1 year. Interest multiplied across, we've got 500x. Now, this is the interest we earned at one of the rates. This is the interest we earned at the other. This is how much interest we want total. So we're going to have the interest we made in one account plus the interest we made in the other account equals the interest we want total. Solving this, subtract our 28 from both sides. We'll get 500x equals 47. Divide by 500. And if you need help with any of these divisions, you might want to ask your group tomorrow. And now notice, this is as a percent, but or as a decimal, we need to change it to a percent and move it 2 spots. So we need to invest it at 9.4%. Notice once you've got the table set up, it's not very hard. The hardest part with these is the table. Moving on to a distance problem. Once again, we're going to need a table. And once again, we're going to have our options on the left. So we've got 2 cars that are driving here. So our options are car 1 and car 2. Now, when we have distance, you probably remember the formula distance equals rate times time. And that's what we're going to use. We're going to use our rate, or the speed, the time that we drove at that speed, and that's going to equal our total distance that we went. So our first car, let's look at the one that's heading north. If you wanted to, you could call this the north car, that's fine. The north car is going 60 miles per hour. We don't know how long he drove, so that's our x. So we've got 60x here. The second car is going south 75 miles per hour. Once again, we don't know how long he drove, so x, 75x. Now, before we get to an equation, let's think about this. They both started here. We had one car go this way, one car go this way. We want to know how long after they left were they 540 miles. So when was this distance 540 miles? Notice this is the distance that the south car went, and this is the distance that the north car went. So it's when together they're 540 miles apart, which means the distance the first car went plus the distance the second car went is our total distance. 60 plus 75 is 135x equals 540. Divide by 135. X equals 4. So remember, it's how long after they left. No, it's our x. So 4 hours. Next up is another distance problem. So let's start the same way. We know we're going to have our rate times our time is equal to our distance. Our options here, we have somebody that's running, and we have someone that's biking. So let's first look at our runner. Our runner is running at 6.5 miles per hour. We don't know how long total he ran. We know he left at 10, but we don't know his total time. So his total distance is 6.5x. Now our biker, he can bike at 14 miles an hour. Now he's not biking for the same amount of time you are. He leaves an hour and a half later, so he's going 1.5 less hours. And so we want to know when they're the same distance. So remember, we've got the runner going this way and then the biker going the same way. So we want to know when they've caught up to each other or when they're the same. So when they've gone the same distance, so set them equal to each other. On the right, we've got to distribute that 14. So we'll have 14x minus 14 times 1.5 is 21. Combine our x's, so let's subtract this 14 over. We'll get negative 7.5x equals negative 21. Divide by negative 7.5. We'll get x equals 2.8. But we want to know what time it is when they catch up. So this is how long has elapsed. First off, we've got to figure out what that 0.8 of an hour is. So, 0.8 of an hour. So we need to figure out what 60 minutes is. A tenth of 60 minutes is 6 minutes. But we need 8 of these. So that gives us 48 minutes. So we know the total time elapsed was 2 hours and 48 minutes from when the first person started, because that's what our x was. So then if we left at 10, after 2 hours and 48 minutes, it's going to be 12:48 p.m. Next up, we've got our mixture problems. We have a store selling different things. They're mixing them together. Start the same way with our table. Option 1 that we're selling is our nuts. Option 2 that we're selling is the chocolate chips. The only thing different here is now we also need a line for our total mixture. Now across across the top, we're going to have our price per pound, how many pounds we've got, and then this is going to be our total value. So let's look at these nuts. They sell for $6 a pound, and we know the chocolate chips are $1.50 a pound, and we want our mix to be $4 a pound. So that one's easy to fill out. Now let's look at the amount of all of them. We want to use 8 pounds of nuts, so we've got 8 pounds. And we are asking how many pounds of chocolate chips, so that's what we don't know. But we're mixing these two together to get our trail mix. So our mix is just going to be how much nuts we put in plus how much chocolate chips we put in. So it's just adding them together. Value is just the price times the pounds. So 6 times 8 is 48. 1.5 times x is 1.5x. And then this is just going to be 4 times 8 plus x. If we want to go ahead and distribute that, 4 times 8 is 32 plus 4x. And now, total, we're adding our nuts and our chocolate chips to equal our mix. So we've got the value of the nuts plus the value of the chocolate equals our total value that we're adding them together, or our mixture. So now let's go ahead and subtract our x and get our x's together. So we'll get 48 equals 32 plus 2.5x. Subtract our 32 to get our x by itself. Divided by 2.5. 6.4 equals x. So we need to add 6.4 pounds of our chocolate. Once again, this is another type of mixture problem. You're not actually mixing two things physically, but we've got two different ideas going on here. So same as before, let's start with our chart. Our two different things we're mixing together here is our plain cheesecake and our strawberry cheesecake. And the different things, we always want to put what we know. So we've got our price, our amount, and then our total value. So let's look at the different cheesecakes. The plain cheesecakes are $10. The strawberries are $15. We don't know how many of each of them we made or sold, but we did sell 37 total. So we don't know how many plain we sold, so we can call it an X. But we know we sold 37 total, so it's 37 minus however many plain we sold, which was X. Because for example, if you sold 5 plain cheesecakes, you would have 32 strawberry cheesecakes. And then this follows from before, multiply across. So our value is 10x, and then 15 times 37 minus x. If you wanted to go ahead and distribute, you could, and get 555 minus 15x. Now these are the value is our money. So we know we made $430 total. So that's how much money we made off the plain cheesecakes, which was 10x, plus how much money we made off the strawberry, which is this 555 minus 15x. Now let's combine our x's. So we'll have 430 equals 555 minus 5x. Subtract our 555. We'll get negative 125 equals negative 5x. Divide by negative 5. X equals 25. And now let's come back. Our x was how many plain we sold, which means we sold 25 plain. And the rest of them are strawberry, which means we sold 12 strawberry cheesecakes. always want to make sure you go back and answer the original question. And this last one is another mixture problem. This time you're actually mixing two things together like we did with our nuts. Start with our chart, the things we're mixing. We have a solution that's 15%. We're mixing the pure acid to it. We want to end up with a 40% solution. Once again, the things we know, that percent, the amount, and this is going to be our total as far as the acid in our solution. So let's fill in what we know. The 15% solution obviously has 15% acid. The pure acid is all acid, so it's 100%, which is 1. And then the 40% is 0.4. Alright, we have 6 grams of this 15%. We're asking how much of the pure acid, so we don't know. But when you pour these together, you're going to have however much you started with plus however much you poured in. And then total, once again, just multiply across. So 0.15 times 6, which is actually 0.9 if you wanted to do the multiplication now. We'll have 1x and then 0.4 times 6 plus x. If you want to go ahead and distribute this, you get 2.4 plus 0.4x. And now, once again, the two things you're mixing equals your total. So 0.9 plus x equals 2.4 plus 0.4x. Let's get our x's together. So we have 1x minus 0.4x. So we've got 0.9 plus 0.6x equals 2.4. Subtract our 0.9. We'll get 1.5 divided by 0.6. 2.5 grams is how much we are adding. The key thing on this whole entire section is remembering those charts and setting them up correctly.